Are you having fun with all the vector identity and manipulations that we need to do for these calculations? Because if you want more, we have more waiting for you right now. The statement reads, Part A, using JF in place of J, show that the Poynting vector becomes S equal E cross H. And the rate of change of the energy density in the fields is du dt is equal to E dot partial D with respect to T plus H with partial B with respect to T. And then for linear media, show that U is equal to 1/2 E dot D plus H times, or H dot B. For part B, in the same spirit, but with rho F for free charge, and JF in place of rho and J, in the same spirit, but with those, don't bother to construct the Maxwell tensor, but show that the momentum density is G is equal to D cross B. Ooh, we had our hands full with this one. Let's dive in. So if we're only interested in the work done on the free charge and the currents, dW dt is equal to volume integral E dot J d tau. So we can substitute in the JF, and but we notice that JF occurs in the Maxwell's equations for the media, with the curl of H is equal to JF plus the time derivative of D. So we can solve this for JF and substitute it in. But the integrand is a dot product with E, so we have E dot, the curl of J, or curl of H, minus D times the displacement field, dt. And then we just distribute the dot product, okay? But we note that we have the E dot curl of H, which we can use another vector identity product or triple product identity. And we have the divergence of E cross H is equal to H dot curl of E minus E dot curl of H. Okay, so we see the purple parts match and we want to solve for that. So although it's not written explicitly in a form that we know, we can algebraically solve for a form that can be useful. All right, so we do that. And then we go ahead and see that we have H dot curl of E minus the divergence of E cross H. So we'll go ahead and substitute that into the integral, and we have H dot curl of E minus divergence of E cross H minus E dot the partial derivative with respect to T of D d tau. All right, but we know Faraday's law gives us the curl of E is equal to negative partial time derivative of B dt. So we can plug that in. And we see here that we have another time derivative, so we'll put the time derivatives together, factoring with the negative out front, split up the integral with the divergence of E cross B, apply the divergence theorem on that second integral, get that down, yeah. And then we have, again, we'll just bring down the partial derivative integral with us after we substitute it in with the divergence theorem. So then we have E cross H dot dA. And sure enough, this is Poynting's theorem for the fields in matter. Evidently, Poynting's vector representing the power per unit area transported in the field is, well, the closed integral. So we have S is equal to E cross H, check. And the rate of change for the electromagnetic energy density is du EM dt is equal to E dot partial derivative of D by dt plus H dot dB dt. For linear media, we know that D is equal to that D is equal to epsilon E and H is equal to 1 over mu B, where epsilon and mu are constant in time. Thus, the E and M energy is, well, if we plug those in, we get dot products with the vector derivative, dot product of the vector with their time derivatives. So we can factor in the 1/2 formula that we used a couple questions ago, take into account with the epsilon and mu's. And so we just put in 1/2 d by dt of their dot product, take the time derivative out, so you get 1/2 d by dt of E dot epsilon times E dot E and 1 over mu B dot B. Plug the epsilon back into the second part of that dot product and the mu to the second part of that dot product, and we get E dot B and E dot H to resub it in. So all we did was work a little algebra magic just to get the 1/2 and d by dt out front. So if we go ahead and cancel that d by dt's on both sides by integrating, we get mu em is equal to 1/2 E dot D plus B dot H. Pretty nice, pretty consistent. Similarly, the force on the free charge and currents, we just go ahead and plug in the force law, so we get rho E plus J cross B d tau. And force therefore goes to rho FE plus JF cross B d tau. And again, if we go ahead and use the Maxwell's equations for media, rho F goes to the divergence of D, and JF goes to the Ampere's law, I believe, in material, which is curl of H minus partial derivative of D with respect to T times B. So we plug those in, again, per unit time, of course. So we have little f. And now we just, so we don't have to integrate. So now we just, move it on through, right? So here we switch the order of E and the divergence of D, since, again, that's a scalar, the divergence is a scalar, so we can move that through. But we need to distribute the cross product, so we have a curl of H cross B, and then we also have minus partial D dt cross B. And again, if we see that the derivative is terms of the form d by dt of d cross b, then we know that that's a product rule, and we see the product in purple match, so we can go ahead and algebraically solve. And what we want to do now is, since we have d by dt of d cross b minus d of the cross product db dt, well, we know that db dt from Faraday's law is equal to negative curl of E, so we get a negative and a negative cancel. And so we go back to the energy or the force equation, and we have E times the divergence of D plus the curl of E or cross B, and then we plug in what we just solved for with the derivative term. So that's d by dt of D cross B minus D times or minus D cross the curl of E. Okay. What we have here is a bit of a dilemma. Not really, but we need to be careful. What we have to do is add in a zero term, okay? And we can do this algebraically, and that's fine, but we do that so that we can reinforce the vector identities, meaning that we have E times the divergence of D plus 0, which we'll rewrite as H times the divergence of B, which we know to be 0, and everything else stays the same, but we only do that so we can have our vector identities for E and D and H and B come to fruition. And so this is the divergence of the stress tensor. Once we add that component in and we see D and E work together, and we have H and B working together, and then times the time derivative. And so the divergence of this is the divergence of the stress tensor, with the last term being minus the rate of change of the momentum density. So with that being said, since we're form matching, G is equal to D cross B.